Hello, class. Okay, so I'm going to talk a little bit about the index of refraction lab. So, like here, we have the written instructions here, but record a little video about it as well. So we'll start out by clicking on the link, and that should open it up. If it doesn't, you can maybe copy and paste the URL into, like, just if some people have issues. But yeah, so there's three options here. We're just going to look at the first one, the intro. So what we have here, we have two mediums. On top we have air, on bottom we have water. And here's our laser pointer, and we click the button to turn it on. So it's like here we have the, we can see it hits. They draw a normal line where it hits. So you can turn the laser on or off. And we can see there's a reflected ray and a refracted ray. We can select the material for the top and bottom. But for now, we're going to leave them as air and water. And what we want to do is measure the index of refraction of water, which is 1.33, but we want to measure that experimentally. So first, we have this protractor tool, which we're going to drag over and place kind of where it belongs. So like the laser hits right at the center. Okay, that looks good. And so what we want to do is we want to collect data. We're going to start, theoretically, you could use this to find the index of refraction of water. You could just pick one angle, like say 30 degrees for the angle of incidence, and then the angle of refraction looks like around 22 degrees. So you could use that one point of data to find the index of refraction. You have, for air, you just have an index of 1. So we have sine of 30 degrees would equal the index of refraction of water times the sine of 22 degrees, and then just divide, and that gives you your index of refraction. But that's just a single data point, and we want to do better than that. So we're going to make a table. So we're going to start at 10 degrees, and then just go through at 10-degree increments, so 10, 20, 30, all the way up to 80. Now, we're not going to do this in the lab, but let's start with a nearly vertical. So the laser just hits the water directly. You can see that this refracted ray is really thin. Or the reflected ray is thin, the refracted ray is much thicker. And then as you change this, the reflected ray gets darker, and the refracted ray stays pretty dark too. But yeah, so this is kind of a measure of the intensity, which we can measure with this device here, which we're not actually going to use in the lab, but, why not just do this? So here we can see the reflected ray, the intensity is about 2.31%. So if you shine light vertically down on a, water surface, not much light's going to reflect. And then if we look at how much is transmitted into the medium, they should add up to 100, so that should be about 97.69, and that's what we get. And then let's look at a much steeper angle. So here we're getting very significant reflection. Let's just say 44%, and then this will be around 56. But again, that's not something we're actually going to use in this lab, so we can put that back. Okay. I guess we can turn off the normal vector if we like, but I don't know why we would do that. So what we're going to do is we're going to make a table. Put that here. So the angle of incidence, we're going to pick those 10, 20, 30, 40, 50, up to 80, and then measure the angles of refraction. And they are related by this, so write down the equation. Bring up this. So what we have is N1, air, it's hard to write with a mouse, but it's an equation you should know. So yeah, we have n1 sine of theta 1 equals n2 sine of theta 2. Now in this lab, we're assuming that n1 is known. We bring the simulation back up. Yeah, n1, it gives us both actually, but we're going to pretend we don't know the index of refraction of water. So n1 is known though. So let's bring paint back up. So we can even erase it in this case. But now we want to, let's look at what data we have. It was this. So we had theta 1 and theta 2. So we have all this data. And we want to use this data, we want to use all of our data to get the index of refraction. So again, we want to plot this, but you can see from Snell's law that this is definitely not a linear equation because our variables are theta 1 and theta 2, and they occur in sine functions. So a linear equation is when it's just the two variables are related by two constants. Really, you have a slope and then an intercept. So it's like one constant is a multiple of the other, or one variable is a multiple of the other plus some offset. This is definitely not linear. So what we have to do is linearize this. And again, we've gone over this a few times, but I know students still sometimes struggle with this. So what you want to do is you want to find x equals and y equals. And if you don't immediately see what to do here, I don't want to give it away, but try to figure it out, how to linearize this data. There's kind of two obvious ways to do it. But work with both of these variables, just like pick something for x and y. And then when you do that, plug it in to the original. So yeah, okay, I'll give you an example. I don't want to give it away, but I can give you like a wrong way to do it. Let's say x is theta 1. And let's say, let me undo that. Let's say y is sine of theta 1. Now, remember our data contains theta 1 and theta 2. So x and y better be related to theta 1 and theta 2. But let's say x is theta 2. And let's check, is this a linear equation now? So here we have sine of theta 1, that's y, equals n2. That's a horrible 2. I cannot live with that one. So, okay. So n2, and then we replace theta 2 with x, so we have sine of x. So now we have a relation between x and y, and it's better than what we had before, but it's still not linear because we have y is n2 times sine of x, and we don't want that sign. So I won't give away like the next step, but yeah, hopefully you can figure out how to linearize it. But there shouldn't be any question once you pick your substitutions for x and y. Because here we plug it back into Snell's law, and we should be able to see immediately if it's linear or not. This one is not. Okay. So once you linearize the data, like let's say we went with this, we would have to have a new table where instead of theta 1 and theta 2, we'd have x and y. So we have a new table. And for our x values, those are just theta 2. We just copy those directly. Theta 2, we have the indexes of, or the angles of refraction for each of those angles we measured. But for y, instead of theta 1, we'd take sine of theta 1 and put it there, and then sine of theta 2. So we can fill, like once you pick your x equals and y equals, you can make a new table, but it's still not good if it's not linear. At least not for what we're doing. Possible to do non-linear fitting, but we're not doing it. So anyways, make sure you're linear, and then you can make your new table and plot that data, and it should be a line. And by taking the slope of that line, so you should have a bunch of data points, find your best fit line, which in this case was pretty thick and completely covered the data points. But anyways, yeah, so you also want to find the slope and possibly the intercept of that best fit line. Okay, you don't need the intercept. It should be 0. I'll give you that much. But you do need the slope, and that should give you the index of refraction, N2. Now, when I say it should give you N2, I'm not saying that the slope is going to be N2, but it'll be related to it. So you might have to do some algebra after getting the slope. So don't just think your slope is your index of refraction. It might be, it might not be. This one is a little bit easier to screw up than most because the index of refraction is a dimensionless number. So when we have our x and y, normally they have units. And so a slope would be whatever the units are on the y-axis divided by the x. And so the units can give you information about what the slope represents. That's not the case here. So, but again, just be careful. Try to figure it out. And the reason we're doing this air and water thing, we already know the index of refraction. So again, you can kind of check and make sure you did it right just by seeing if your equation is linear. But then once you do it, you should, like, the errors are going to be pretty small, just these tiny measurement errors. So the index of refraction you get from the lab should be very close to 1.33 for this part, doing the air and water mix, or those two mediums. Okay. And now because we have an accepted value and we have a measured experimental value, then make a table and just compare them. So it'll be one of those n. Oh, wait, that's the wrong thing. We'll have like n experimental. Now this one, we don't really have a theoretical value. It's another. So we could call this the n accepted. So we have an accepted value, which is 1.33. And then we want a percent. We can call it an error in this case. So there's that thing between percent difference and percent error. Let's call this a percent error because we're assuming that these values we see in the book are measured carefully. And so we can consider 1.33 to be an accurate measure of the index of refraction. So if we get something different than that, we can call that an error instead of a difference. Okay, so part 1, that's the idea. And we're doing part 1 because we're trying to measure the index of refraction of a known material. And so if you do that and get it, you check it, if you get 1.33, then you're doing everything right, pretty much. I think it'd be unlikely that you could get the right answer and screw something up in a major way. So this is kind of like a confidence builder. And then what we're going to do is we're going to start over, but we're going to change material to, you can pick either mystery A or mystery B. I don't care what you pick. Now they don't tell you what N is. So now we're going to repeat the procedure. Go 10 degrees, 20, 30, all the way up to 80 degrees, and measure these indexes of refraction and find this unknown N. So we're going to leave the top air, and now the bottom is going to be one of the two unknowns. You can pick whichever you like. And yeah, we're going to do the exact same thing except for the very last step, because we can't do this table for part B because we don't have an accepted value. We're trying to find out what the value is. We have nothing to compare it to. So at the end, once you get your index of refraction, that's like your conclusion. Just make it out like my index of refraction for this unknown material is, and then just whatever it is. I will say one more thing about the linear fitting. One kind of common source of error is getting the axes mixed up. And again, if you pay attention to units, that shouldn't happen. But in this case, it could because they're dimensionless. So we have one other fact we can use to avoid screwing things up. And know that the index of refraction has to be greater than 1. In general, it's greater than or equal to, but it's only equal in a vacuum, and we're definitely not dealing with that case. So your index of refraction is greater than 1. So if you kind of screw up the getting the x and y properly, sometimes students will get, instead of using the slope, or instead of using like 1 over the slope, they use the slope. So it's flipped upside down. So if you get an index refraction less than 1, look at your x and y axes. That's probably what happened. All right. So yeah, there's 2 parts of this lab. One is the index refraction of a known material. You can just leave it air and water. If you want to pick another known one, that's fine. But just indicate what it is. And then for part 2, pick either the unknown A or unknown B. And it's the same procedure for both, except for part B. We don't, or part 2, whatever we call it. We don't have that percent error because we have nothing to compare it to. So that'll be it for this lab then. And this is the final lab. And I'll make it do a week from now, but I'm not posting this till Friday night. So I'll say a week from Saturday. So when would that be? So yeah, that'll be due on the 8th. And again, if you have any issues with the lab, just email me and can help you out with that. Okay, so that'll be it. Just let me know if you have any questions about this lab.